So the prior video, we motivated the idea of matrix row operations, meaning that we can work with matrices and reduce them down using operations. Let's illustrate this process briefly with a simple matrix like 1, 2, 0, 4, let's say. So notice that I can do things to this matrix using the three operations we've discussed. The goal is, can I reduce this matrix down to something that looks like this or something else? The idea being, of course, I want to make it look like the identity matrix or something that at least looks like an identity matrix. The way that I do this conversion is through a series of row operations. First, I see here that these are okay. I have the same number, so I don't need to do any row operations. But what I can do is make the bottom number look like this here by dividing the bottom row by 4. And remember that we don't alter the solution by multiplying entire rows by numbers. So if I have 1/4 of row 2 here, then I convert this matrix into 1, 2, 0, 1, because 0 divided by 4 is 0, and 4 divided by 4 is 1. Now the next question is, how do I get rid of this 2? And the answer is very easy. Remember that the next operation that we can do is that we can add scalar multiples of other rows. So notice that you have a 1 here and you have a 2 here. Therefore, to get rid of the 2 over here, I can multiply the whole row by -2 first. So do -2 times row 2, which will get me 1, 2, 0, -2. And then set row 1 equal to row 1 plus row 2. So 0 plus 1 is 1. -2 plus 2 is 0. And we're left with nothing has changed on the second row. But now what you can do is divide -1/2 of the second row, and we get our solution here. So what have we accomplished here? We were able to convert one matrix to something that looks like an identity matrix, and in this case it is, by using our what's called reduction or elementary row operations. And again, these are motivated by the basics of just regular algebra when we talked about systems of linear equations. Let's formalize this, and this process is what is referred to as Gauss-Jordan elimination. And here's the idea. We start with a matrix. Let's say 2, 3, 4, 6, 7, 9, 1, 1, 1. And the question is, what does this reduce down to? So the first thing that we always do with Gauss-Jordan elimination is we try to get a 1 up in here. So here's the general rules for Gauss-Jordan elimination. To convert the matrix down into a form that looks something like the identity matrix, the first thing we do is try to conduct a series of operations that will put a 1 up here. Once we do that, we then proceed to conduct additional operations to turn all other numbers 0. We then proceed to try and turn the next number in the diagonal equal to 1, usually by division. And then we try to convert this number, and any other numbers to 0, again, using the operations. And by doing this procedure, going from left to right, converting the diagonals to 1, we'll be able to get something that might look like the identity matrix. And if it does not, then we know that the vectors are linearly dependent. So let's apply. First, we know we can switch rows. So switch rows 1 and 3. So we have 1, 1, 1, 6, 7, 9, and 2, 3, 4. Next, turn these to 0. Remember, once you get a 1 here, the next step is to turn all the other numbers in that column. We call this a pivot, by the way. To turn all those numbers in that column equal to 0. And the way we do that is by looking at scalar multiples. So how do I convert the 6 to a 0? Multiply the whole first row here by -6, and then add each one to here. So -6 times 1 is -6, plus 6 is 0. -6 plus 7 is 1. -6 plus 9 is 3. And then we're left with the 2, 3, and 4. How do we convert this to 0? Same thing. Pick row 1, multiply by -2, and apply each one to each corresponding value. So I still have 1, 1, 1, and 0, 1, 3. -2 times 1 plus 2 is 0. -2 times 1 is -2, plus 3 is 1. -2 times 1 is -2, plus 4 is +2. Okay, now the next step is get the next diagonal element to equal 1. Well, it's already 1. Life's good. We don't need to do anything. So what do we do now from here? We do the same thing we did for the non-pivot items. How do I get rid of this 1? Multiply this whole row by -1, and then apply it to this row. So here we have -1 times 0 plus 1 is 1. -1 times 1 plus 1 is 0. -1 times 3 plus 1 is -2. And then we do the same thing, but on here. -1 times 0 is plus 0. We just get, of course, 0. This doesn't change, by the way. We just keep that row. 0. -1 times 1 plus 1 is 0. -1 times 3 plus 2 is -1. Okay, now notice we have all zeros in the column. We move to the next column. One pivot, one next diagonal, okay, down. Here you notice we don't have a 1, we have a -1. So we need to divide the whole row by that number to clear that out. -2, 0, 1, 3, 0, 0, minus, I'm sorry. When we divide or multiply, whichever way you want to look at it, when we multiply the whole row by -1, we just get 1, and we're left with that. Okay, now get rid of these two using the same rule, but using this as the pivot. Multiply. How do I get rid of the 2? I add that with a +2 over here. So multiply the whole row by +2. Here we're keeping this the same. We're keeping this the same. This top is now changing. 2 times 0 is 0 plus 1 is 1. 2 times 0 is 0 plus 0 is 0. 2 times 1 is 2 plus -2 is 0. Okay, now we got to get rid of the 3. We do that by multiplying -3 times the whole row and adding. 1, 0, 0, 0, 0, 1. 0 times, -3 times 0, 0 plus 0 is 0. -3 times 0 is 0 plus 1 is 1. -3 times 1 plus 3 is 0. And as it turns out, we get a reduced matrix. So in this case, life is good. The Gauss-Jordan elimination, this is Gauss-Jordan elimination in a nutshell. Basically, what we're trying to do is convert the matrix into something that either exactly looks like the identity matrix or something that at least resembles it. Now, why is this important for independence of vectors? We'll talk about that in the following video.